Good afternoon. We are Team Uno, so named because at the beginning of this, at the beginning of Momentum, we were Team One, and we also decided to utilize the Arduino Uno. My name is Joseph Coleman, and I am planning on majoring in physics.
My name is Miguel, and I'm a freshman. I'm considering majoring in biological engineering.
My name is Danielle. I'm a sophomore, and I'm currently course 6, which is computer science and functional engineering. Okay.
My name is Isaac Garza. I'm a current freshman declared as course 6-2, which is computer engineering.
My name is Fernando Jordan. I'm a freshman, currently undecided, but I'm between mechanical engineering or electrical engineering or computer science.
So here's the agenda of our presentation today. We will go through the challenges, the planning we did to successfully complete the tasks, such as the camera swivel, the popping mechanism, the circuit interface. We'll go over the costs, the skills needed to complete the project, what we learned, and closing remarks.
So, as you've heard several times, there were two main challenges. We had the 5-pronged obstacle course where we had to navigate a quadcopter through 5 loops of different heights. And then we also had an interface challenge where we had to identify 2 sensors of unknown locations. We had to avoid a danger zone, and we also had to take pictures of 2 separate images. I just want to say quickly on another third challenge that the Momentum also presented is, and one that I feel is underappreciated, is the fact that we have to give a presentation both to our peers and to judges. Public speaking is a very important skill, and it is challenging to give a comprehensive and succinct presentation without boring the pants off of people. So I want to thank you for that as well.
With that, we see our final design for our quadcopter. When we first started Momentum, the OME gave us an assignment. It said that we must complete the challenge that was before us, and the motivation behind our design process was not to design the best solution, but to design the optimal solution. Because we were aware of the fact that in this month we had constraints. We had a team of people who, the most of us, we had never worked with each other before. We had a limited amount of time, we had a limited amount of resources, we also had a limited amount of expertise. So while it is true that you could dive into certain areas of the assignment and try to do something theoretically, it's best to take into account what expertise you have to design your optimal solution. And inside of our solution, we decided to pursue, based on the point values, because this was a competition, we wanted to go for the multipliers which we felt our expertise could fulfill, and we wanted to make sure we had a reliable product. So that led us to design various parts of the quad rotor, such as a swiveling mechanism, our popping apparatus, and our circuit interface, all of which you will hear of, and I'll pass it to Danielle for the camera swivel.
So the swivel mechanism. From the beginning, we knew that we wanted to go at least for the no line of sight multiplier, if not autonomy. But like the other teams, we wanted to have a plan B and secure that plan B first. So we originally decided just to focus on the no line of sight, and then also being able to take the pictures in the interactive challenge. So for those, we decided that it'd be extremely useful to be able to orient the camera wherever we wanted to. So we came up with the idea, as another team did, to have a camera swivel, and for that we used a servo. And originally we had an idea to use like a belt and pulley kind of mechanism where the belt would be attached to the servo and the belt would also be attached to the camera and spin it. Then Fernando just came with the idea that it would just be easier just to directly attach the servo to the camera and then turn it that way and have the servo connected to the Arduino. And so this is our CAD model. That's the picture that we took on competition day yesterday, and that is what it looked like. We 3D printed it. And actually, and you can see it there, it looks and works really well, and it, yeah, we were very successful yesterday. We made a mistake of not flying it with the GoPro stream before, enough ahead of time in the competition, so we did it for the first time 3 days before the competition, and realized that the delay was so much that we couldn't really accurately control the Phantom because you need a lot of adjustments, very small fine adjustments to make sure that it doesn't pull off course. So that was a really big setback for us. And because we only have 3 days left, we decided not to do autonomy because we would go insane and we didn't know that we could tackle that, although we knew that if we had more time we could, but we didn't think that we could do that in a couple of days, so we decided just to do what we could and do it with line of sight, which was maybe a little bit of a disappointment, but still, the cameras will prove useful for the pictures, and we got a good picture, as you can see that. So now I hand it off to Miguel to talk about the popping mechanism.
Yeah, so for the interactive challenge of the project, we have to come up with a design to allow the phantom to pop the balloon and sense the gas that was contained inside the balloon. So initially we were thinking of designing a dual arm claw with a needle attached at its center. So basically the purpose was to open the claw, to program the claw using the Arduino and a servo, so that it could open, grasp the balloon, and automatically pop it with the needle that was attached inside of it. But due to the time constraint and other factors, we decided that, probably we could come up with a better, more efficient way of approaching this. So then we thought about using a simple vacuum that would suck in the air and, allow the gas to be detected, because the phantom produced a lot of wind. It produced a lot of air, and we were afraid that the air was going to push away the gas as the balloon popped. So then we were thinking of installing a simple vacuum that would suck in the air and prevent the gas from escaping. But then we finally came up with another more simple solution, which was to simply horizontally project a long stick of foam, of styrofoam, which was efficient because it didn't weigh a lot. It was very light, and the long projection prevented the gas from escaping because, you see, the wind would blow downwards, and this long projection surpassed that. It went beyond where the wind was pushing down. So when the needle popped the balloon, the gas was very close to the sensors, and the sensors were able to detect what kind of gas was contained inside the balloons. And for the needle, we used a steel grinder, and we really made sure to sharpen the metal rod. We cut the metal rods and we converted them into needles by grinding them and making them really, really sharp.
So having all these parts is no good if you have no way to communicate with it and actually control it. So in order to control it, we use the Arduino Uno that Momentum so kindly provided to us, and just added a pair of radio frequency transmitters and receivers. They are USB connected, so you could simply connect one to the Arduino and one to the computer and have it communicate via a serial terminal as you would if the Arduino was controlled directly. So that was a pretty simple setup to do, and by simple I mean it took only like one whole day to actually understand how it worked. And yeah, then we started experimenting with the circuit design. It started with a really simple plugging in the pins that were assigned by schematics, but we soon ran into problems because at first we just added plug-in straight to the computer, and the computer provided enough amps to actually operate the whole mechanism. But once we started adding servos and the sensors and the radio frequency transmitter, which needed to be on all the time, we realized that the 9-volt battery supply wasn't enough to power everything with a steady amount of current all the time. So we had to add another power supply, which we just use another 9-voltage battery to power directly the servo and not put so much strain on the microcontroller. Because of this, the actual circuit design became more expansive than what we originally thought, and we originally had thought that we could fit it inside the UAV. But as you can see, it's pretty compact, so we opted to mount it instead underneath the Arduino underneath the UAV and next to the payload. And this also provided the extra advantage that it was easier to directly modify if we ever run into problems, which we did. So to secure all the connections, we use engineering's best friends, duct tape, electrical tape, and zip ties. We put all the cables that were close together, we wound them up with tape and use a zip tie to secure, so there wouldn't be as much access of freedom. And the long cables were glued onto the breadboard. But the Arduino itself is only held in by tape, so it's completely reusable. And then we also added extra plastic to the back, as you can see, to prevent any pylon or obstacle accidentally pulling a cable out. And to actually connect the sensors, we use alligator clips and soldered another cable to the end, so we could connect it directly to the breadboard. And with some extra circuit design and resistors and voltage dividers, we were able to have everything running correctly. In that picture up there, you can see the interface. It basically worked by sending a direct stream two-way communication between the Arduino and the computer. We will be able to control the servo by just pressing A and Q, and we will receive the sensor information real time, all the time. So as soon as you pop it, we will see the voltage drop and be able to, by our knowledge, decide if it was Windex or Clorox. I will now pass it to Isaac, that will explain the cost breakdown.
So at the outset of this project, we wanted to make as many real-life applications, real-life decisions as possible. And one of the biggest things to take into consideration with any project, especially on a much larger scale, is budget. It's easy to say, oh, I can build, this biggest, baddest machine that performs up to expectations with $1 million or $2 million or what have you. But being able to be frugal while still maintaining efficiency is something that's very valuable, especially in the corporate world. So we paid for a pair of radio frequency transmitters and receivers, which Fernando just talked about. They're the most expensive, if you'll notice, in our budget, because one thing that we did want to prioritize was having proper communication between the Arduino. It doesn't matter if we have a really expensive servo, full rotation, half rotation, doesn't matter if we can't properly communicate and receive information from the servo and from the sensors. We just bought a standard Radio Shack servo. We bought one that was old enough torque to move what we needed to move. And then everything else, the foam, the alligator clips, the 3D printing, were all resources that we had at our disposal and we utilized thanks to our sponsors and the OME. So we spent a total of $56.10, and we had $43.11 left over.
All right, and with that, yes, given this project and given the constraints that we had, there were certainly lessons learned. For this project, as I brought up before, there was certain expertise which was needed to accomplish various tasks, and we're just going to go through our team now and say the different things we brought to the team and lessons which we did learn. Myself, I did not have much experience at all with coding or design processes or building of anything really. I'm someone who, throughout this experience, I've noticed I'm much more of a theory person. I like theory a lot. Everything always works because you assume that, given that this works, this is that. So it's interesting seeing the part that, expands some time before you get to the nice stuff. Anyway, it was interesting seeing how inside of that design process, how you have to make sure to test all of your different products, all the different components to your final project to ensure that they actually are going the way that you said they should. And so you also have enough time to change your decisions, because before we decided on any of our specific mechanisms, we had gone through an entire list of options. And if we were to have tested the options which we chose earlier on, we could have went back and said, okay, so we see that this actually didn't work, and go back to some of our previous suggestions.
So I contributed with the design, especially with the popping mechanism. Through the process, I learned a lot about chemical sensing, especially about the specific chemical sensors that we use. I learned a lot about the single-wall carbon nanotubes and how they work to conduct and to help to detect gases that are in the environment surrounding the chemical sensor. It was a very interesting experience, and I see how this could apply to real-world issues. So yeah.
Again, my name is Danielle. Coming into this project class, I had a decent amount of coding experience, but hadn't really ever worked with putting things together, working with my hands, which is something that I really enjoy learning, and I'm considering maybe doing more things in course 2 because of it. I learned a lot about the Arduino, which I didn't really know about before, and microcontrollers in general. I'm sure that knowledge will help me in the future. I learned about breadboard, which surprisingly I had never used before, and it's really exciting because now I'm probably going to buy my own Arduino and do stuff with it. It was a really good experience to work with a team and a project that had a deadline to learn how to work together and how to communicate. Learn how to get over bumps in the road if things didn't work the first time, not to give up and try again, and I don't know. It was really fun. The thing that I really liked is working with my team, and I enjoyed this project and learning everything that I did.
Again, my name is Isaac Garzad. I brought some basic coding experience in Java that I had taken through high school, as well as some general circuit design suite and breadboarding experience. However, most of my building experience was with larger woodworking and metalworking projects. So something of this scale, mostly integrated with electrical components, wasn't something that I was used to at all. I definitely took away the experience of having to build a relationship with a team and perform to expectations or beyond, all under a budget and a deadline. It's difficult when you first meet people to know, what they're going to be good at, what you're going to be good at, and how you're going to work together. I feel like in the end, we came together, like Danielle said, there were some bumps in the road. However, it was a good experience and it was a good project that is definitely applicable in real world situations where you're never going to be, almost never going to be, on a team with your best friend or someone who you've known for several years, or someone who you may even like at all, but you have to get through it. And I like all of them. We're all friends.
So I brought some mechanical design expertise, basic interfacing through microcontrollers, which I have picked up in high school, which I did one robotics competition. And during the actual project, I learned about computer-aided design, 3D printing, and basic circuit design. I also learned how important it is to plan ahead, noticing there's going to be a lot of minor bumps that you're not going to see. For example, a flipped battery, which no one notices, and just makes your circuits go wacko. Things like that take a lot of time, even though the problem is really simple.
And to conclude, again, we just want to thank all of our partners, especially our sponsors, and we wouldn't have been able to do this without you. So